Okay, so welcome to all of you. Now we'll discuss, that is, we'll revise the subspaces. Okay, so first we will see what do we mean by a subspace. Okay, so suppose V is a vector space, W is a non-empty subset of W is non-empty subset of that V. That means a non-empty subset W of a vector space V is called a subspace if it is itself a vector space. Under the operations defined under the same vector addition and scalar multiplication as defined for V. Okay, so that means whatever the operations are defined on V, that operations are also defined on V, and W should be the vector space with respect to that addition and scalar multiplication which are defined on V. Okay, so W is the non-empty is important here. Okay, so that means here one thing is note that, so 0 vector of W and 0 vector of V both are the same. Okay, whatever the 0 vector of V is there, so that is also a vector, that 0 vector is in V. Okay, so note that this same thing as a negative vector also. So this is very important here. Okay, so now what is the criteria, how to show that W, suppose W is the, note that this is the subset. If it satisfies all the 10 axioms, then that is called a vector space. Otherwise, no. Any subset will not be a vector space. Any subset will not be a subspace of V. Any subset of V need not be a subspace of V. If it is satisfy all the 10 axioms of the vector spaces, then it will be a subspace. It will be a vector space because it is the subspace of V. Okay. So 0 vector of V and 0 vector of W are same. So what are the criteria? So first, W is not empty, suppose. That means what? 0 bar belongs to W. This is the first condition. Second condition what? Well, take any two vector and show that U bar plus V bar belongs to W. Take any two vector from the W, show that their addition is also in W. That means W is the closed with respect to addition. When we say that W is the closed with respect to addition, whenever W, U bar, V bar belongs to W, U bar plus V bar is also belongs to W. Then this is what? W is closed with respect to vector addition. Okay, it is called. Then third, K is any scalar. Suppose K is R. So all are vector spaces over R. Okay, so R means this is what? Any field now. You can take any field K here. Okay, so U bar belongs to W. So K is the scalar. Then K U bar belongs to W. So this is called W is a closed with respect to the scalar multiplication. W is the closed with respect to the scalar and with respect to vector addition. This is addition, this is the scalar multiplication. If W holds these two properties, then W will be the vector. No need to check other property. Show that what? W belongs to 0 bar belongs to W. Take any two vector from W. Show that their addition is also belongs to W. Take any scalar, take any vector from W. Show that their the scalar multiplication belongs to W. If you prove these three axioms, if W satisfies these three axioms, if W satisfies these three axioms, automatically W satisfies all the 7 axioms. That means W is a vector space if W satisfies this. Okay, this range. So that means W is a subspace of V. So W is subspace. So only these three axioms are there for W. Okay, these are the three criteria. If these three criteria hold W, then W will be the subspace. Okay, so remember this. Also, W is non-empty means what? W is not empty. Then what? Alpha, beta. This U bar, alpha, beta belongs to, suppose this is K is the any vector field, suppose. A is the field, K is the scalar field. Okay, and U bar, V bar belongs to W. Okay, so if alpha U bar plus beta V bar belongs to W, for any scalar alpha and beta, U bar and V bar belong to W. If this is what, then W is also subspace. Okay, this is what W is the subspace. So this is what, then W will be the subspace of V. Okay. So these are the two important axioms for this. Now we see some examples on this. Okay. So subspaces of R2. Which are the subspaces of R2? So W1 is the singleton 0 vector and W2 is R2. Except R2. and W3 is equal to xy such that ax plus by is equal to 0, AB belongs to R, whatever this. That means what? Any line passing through origin. Any line, this is what? Any line passing through origin. This is R2. These are the subspaces of, examples of the subspace of R2. So what are the subspaces of R3? Singleton 0 bar. So this is W1. W2 is R3. And W3 is what? Say line through origin. Line through origin. That means what? 3-dimensional line passing. Okay. And a plane. And plane passing through origin. Plane passing through origin means what? X plus by plus cz is equal to 0. X plus by plus cz is equal to any type of the equation. Suppose what? W is equal to x, y, z. Suppose twice x minus 3y plus 4z is equal to 0. If your W is like this is the subset of R3 because what? All x, y, z are not there. Or which x, y, z which satisfy this condition, that will be your or that points will be in your W. So W which point from R3, so that satisfy this condition. The condition is there what? Twice x minus 3y plus 4z is equal to 0. So this will be the vector space. Okay. So even though if you write this twice x minus 3y is equal to 0, this is also a subspace. This is also subspace. Even though if you write x is equal to 0, it will be also a subspace. Okay. Note that in this. These are the subspaces of R3 now. Now we'll see some examples of the subspaces. Okay. Suppose W is equal to x, y, 0. So x, y belong to R. So this is what? The subset of R3 now. So that means here what? Z is equal to 0. Z is equal to 0. This is the plane passing through origin. This is the plane passing. So this is the subspace. This is the subspace. Suppose W is equal to xyz such that x is equal to 4y is equal to 4y plus z. Okay, x is equal to 4y plus z. So this is what, if you shift all these things, this is the plane passing through origin. So 0 bar belongs to this one. Okay, and this is the plane passing through origin. It is the subspace. So if W is equal to xyz such that x raised to 4 is equal to y raised to 4. X raised to 4 is equal to y raised to 4. So is it a subspace? How you can check it is a subspace? So what here? For any, suppose if I take here, this is not a subspace. Because what? Because if I take u bar is equal to suppose 1 minus 1 and v bar is equal to 1 1 suppose. Okay. So here what then? X raised to 4 u bar v bar belongs to W because what? X raised to 4 is same as y raised to 4. X raised to 4 is same as y raised to 4. But what about u bar plus v bar? U bar plus v bar is equal to what? 2, 0. So here what? X raised to 4 is not same as y raised to 4. Right? So that means what? U bar plus v bar do not belongs to W. So this is not a vector space. Something like this x raised to 4 x square plus y square, something like this, that will be not a vector space. Note that. Okay. So here if it is the x square product is there, it will be not a vector space. Note that. So that means what? Suppose this is what? If you write this x y z such that yz plus w is equal to 0. This is not linear. Okay. It will be also not a vector space. Note that. It will be also not a vector space. Okay. So if there is a product, so by observation you can check this is not a vector space. Okay. Now suppose this is what? X0. So this is what here? X belongs to R. So this is what? 0 y. Y belongs to R. So xy. X0 means what here? Y is equal to 0 means line passing through origin. 0 means what here? X is equal to 0. Line passing through origin. Okay. So that means this is the subspace. This is subspace. one of the coordinate is 0, then it will 101% it will be the subspace of V. So if W is like this, x, y, x is greater than equal to 0. X is greater than equal to 0. So x is positive, negative, something like this. So what happened? This is what, suppose you are minus 1 into xy now. So this is what, minus x minus y. Okay. Suppose x is greater than equal to 0. Because your xy is in W, means your x is greater than 0. So minus x is what then? Less than 0. Minus x is less than 0. So this is not an element of W. This is not, it is not closed with respect to the scalar multiplication. No problem for the addition. Addition is hold. It is closed with respect to addition because sum of two positive number is positive. But here what? K may be a negative number. So K may be a negative number. Okay. And this xy, x is positive, but K may be, you can take K is from R. K from R, K is the scalar. You can take any K. Okay. So if your K is negative, then Kx, then your Kx. Kx, no guarantee for Kx now. Because x is positive, but no K, but we don't have the guarantee about the K. It may be negative. Then what? Kx may be negative. So that means if such type of this greater than equal to 0 or less than equal to 0, so even though if x is less than or equal to 0 is there, such type of the condition there, it will be not a vector space. Okay. So now you know that this is what f belongs to V. V is what? Set of all continuous function or set of all functions defined on closed interval such that f of half is equal to 0 now. F of half is equal to 0. So then the W is a subspace. Then W is a subspace. Suppose your W is like this, x, y, z, such that x plus y plus z is equal to 0. So this is what? A plane passing through origin. This is a subspace. So if I given this x, y, z such that x square is equal to y square, or I have given this x square minus y square is equal to 0. X square is equal to y square means x square minus y square is equal to. This is not a subspace. This is not a subspace. So one thing is that if W1 and W2 are the subspaces, if W1 and W2 are subspaces, then 101% intersection is a subspace. Intersection is a subspace. But we don't have the guarantee of union. This may be a subspace or may not be a subspace. May or may not be a subspace. Right? This is the difference. But in general, W1 union W2 is not a subspace. Okay? In general. Okay, so we'll do like this. Suppose we'll take examples of W now. And just when I am writing here conditions, Okay. So suppose we have these sets and we have to check whether it is a subspace or not. Okay. Now here what? Y is equal to 1, Z is equal to 1. So you should have value of Y is equal to. So what about 0 bar? 0 bar do not belong to W. Because what? 0, 0, 0. You want Y. This is actually what? Actually this is 1, 1, 1. Actually this is what? X 1, 1. You can write this off the form now. X belongs to R. Okay. So X 1, 1. That means your Y coordinate 1. That means what? 0 bar do not belong to W. W is not a subspace. So this is not a subspace. So now one of the coordinate is 0. No problem for this. This is the subspace. Now this is what? X plus Y plus this is what? X plus Z. That means X minus Y plus Z is equal to 0. This is the plane passing through origin. It is the subspace. Now here what? 0 bar do not belong to this. Because what? 0 plus 0 is not 7. Okay. So that means 0 bar do not belong to W. W is not a subspace. So this is not a subspace. Check for this 0 bar. See here 0 bar belong to. This is what? Y minus 3x and this is what? This is the line passing through origin. So this is a homogeneous system. If W is a set of a homogeneous system, then it will be the vector space. So this is a vector space. This is a homogeneous system of x, y, z. Okay. It is the here what again 0 plus 0. So this is not a plane passing through origin. And also 0 bar do not belong to W. Do not belong to W. W is not a subspace. Here what? 0 x square is there. X square is there. So this is also not a subspace. Something like this. Again here what? 0 bar do not belong to W. Here what? 0 bar do not belong to W. Because what? 0, 0, here 2. 0, 0, 2. Okay. So that means 0 bar do not belong to W. Okay. So that means what here? W. This is not a subspace. Again here 2. Your Z coordinate is always 2. So that means 0 bar do not belong to this. Look at 0 bar. Do not belong to this. Is not a thing. Now this is x, y. This is x minus twice y. So this is a linear equation in terms of x and y. So it is a subspace. So this is a subspace. Because what here? This set is also like this. What? X, y, z. Such that z is equal to x minus twice y. Z is equal to x minus twice y. Right? So this is the subspace. So this is the, because what? This is the plane passing through origin. So this is the subspace. Now linear combination. Linear combination means what? Suppose u1 bar, u2 bar, un bar are the vectors in a vector space V. Okay. Then a vector a u1 bar plus a2 u2 bar plus an un bar. Just like whatever the value of a1, a2, it may be 0 or may not be 0, may be positive, may be negative, whatever it may be. So this vector is called a linear combination of the vectors u1 bar. Okay. So I denote this is what u1 bar. So what is the u bar? U bar is a linear combination of vectors. Suppose this set is S now. Suppose set is S, which is the subset of a vector space V. Okay. So then u bar is equal like this. So this is u bar is called a linear combination of the vectors in S. That means what? Suppose this is u bar, this is v bar and w bar. So whatever you want, take twice u bar minus 3 v bar plus 4 w bar. This is called a linear combination of vectors. See, a linear combination of the vector u bar, v bar, w bar. Take any scalar and multiplication and take the addition, subtraction, whatever you want. So that is nothing but a linear combination. Okay. So now the set of all such a linear combination. Okay, we'll say yes is what? The set of all linear combinations. So suppose this is S1, u1 bar plus a2 u2 bar plus an un bar. So a1 a2 an belongs to R. So now what? The set is depend on a1 a2 an. So set is not depend on u1 u2 because u1 u2 un bar are the fixed. Okay, and we have collected all the linear combination in S. Then S is called this is S. S is called this set. This is not S actually. We call this S. Okay. So this is the set of all linear combination. We call this as L of S. We call this as L of S. Means what? The set of all linear combination of the set of the linear combination of the vectors in S. Okay. So we have collected all the linear combination of the vectors in S here, and that set is called L of S. So this is denoted by L of S. So that is what? Linear span of S. This is also called a linear span of S. This is called linear span of S. The set of all linear combination of the vectors in S. Okay. Now this L of S, this one. That means what? Suppose L of S is what? Suppose your S is what? 1 0 1 0 0 1. Suppose this is the vector. And what is the L of S then? L of S is what? You have to take the linear combination. What? X 1 0 plus y into 0 1. Second vector y is 0. So this scalar, these are the scalar. This is belong to R. Okay. So what is this then? This is what? X y. So x y belongs to R. Okay. So suppose your S is what? Suppose 0 1 1 1. Suppose, and you want L of S then. Linear span of this. L of S is what? X into 1 0 or 0 1 plus y into 1 1, and what is this? X y belongs to R. So this is what? Just to simplify, this will be y. Okay, and this is what? X plus y. X y belongs to R. This is okay. So if L of S is what? So all the vectors are from R2. Okay, your S is what? Your S is what? Subset of R, subset of V. Then L of S is also. So what your S is a subset of V. L of S is also a subset of V. Okay. So now L of S is a subset. If subset is there, then subspace. So you know that S is not a subspace. It is a subset only. But L of S is a subspace of V. L of S is always a subspace of V. Okay. L of S is always subspace of V. Okay. That means L of S is not satisfied the condition of the all 10 axioms of the vector space. But L of S satisfy all the axioms of the vector spaces. Okay. L of S is the vector. L of S is the vector space. That means L of S is the subspace of V, and not only the subspace, it is the smallest subspace of V. L of S is the smallest subspace of V. Note that. And also note that L of S is the independent, dependent. We don't know about anything about the linear dependent, independent of this. Okay. So whatever the S may be here, but L of S is a subspace. This is a guarantee. L of S is the smallest of it. We don't have the guarantee of the L of S is whether it is independent, dependent, basis, something like this. Don't bother about that. Just bother about that L of S is the subspace of smallest subspace of V. Just simply the subspace of V also. You can. Also the L of S need not be V, need not be, maybe V, need not be, but L of S is V. L of S is V. Note that this. That means what? Linear span of the linear span is a vector space V. This is okay. So this is now L of S is the subspace. So this is clear to you. Okay, one more thing we will do this problem actually. Suppose W is equal to, we'll take also examples of vector spaces such that mod X is equal to mod Y. Then W is equal to XY such that XY is equal to 0. Then W is equal to XY such that 3X is equal to 4Y. W is equal to XY such that X square is equal to Y square. W is equal to XYZ such that X plus Y plus Z is equal to 1. So which are the subspaces? This you should know. Okay. Now mod X something like this, it will not subspace because the scalar property do not hold. 0 bar belongs to this, but here what? Mod of Kx Ky, because what here Kxyz is same as what? Kx Ky Kz. Okay, so mod of kx is same as mod of ky. Your mod x is same as mod y. But this does not imply that. This does not imply that mod of kx is same as mod of ky. This does not imply that. Okay, so note that this. So this is not a. Okay, also u bar plus v bar also do not belong to this. It is not closed with respect to addition also. It is not closed with respect to addition also. Because what? So if u bar is equal to 1 minus 1 2 and v bar is equal to minus 1 1 minus 1 minus 2 2 minus minus 2 minus 1 3 suppose. Okay, so your what mod x is same as mod y. For this mod x is same as mod y. This also this is what. Okay, we will take 2 now. This is 2. Okay, here also mod x is same as mod y. But what is u bar plus v bar? U bar plus v bar is what? Minus 1. Okay, here I will take minus 1 also. No? Minus 3 5 minus 1 minus 3 minus 5. So here what? This is not same. That means what here? U bar plus v bar do not belong to V. So if mod x is there, sin x is there, cos x is there, so that means function is attached, then it will be not a subspace. Note that. So for other one, product is there xy, so that is not a subspace also. Here it is a subspace. Here x square y square there, it is not. So 0 bar do not belong here. It is not a subspace. Okay. So one thing is that now here. Linear combination. So determine which of the following. Determine which of the following is a linear combination of u bar is equal to 0 minus 1 2 plus v bar is equal to 1 3 minus 1. So options are given to you 2 2 3 1 5 1 2 3 1 1 3. Suppose these options are provided to you. Okay, so you have to choose which is the linear combination. Which is the linear combination is what? 2 2 2 is equal to 0 minus 1 2 1 3 minus 1. Okay, here you have to choose the sign. So that here you want to, that means you have to multiply by 2 here and you have to add this. Okay, this is only one option to get here 2. This is only one option to get. But here what? You don't get a second component. You get a second component. That means what? 2 2 is not a linear combination of this one. Okay, so for 3 1 5, for 3 1 5. So this is what? 0 minus 1 2 plus or minus whatever this. This is 1 3 minus 1. 1 3 minus 1. Because of the 0 here, you should, this is 1. Okay, so this should be the 3 then. This should be the 3. Right? This should be the 3. So this is again your what? You get a first component, but you don't get a second component. So 3 1 5 is also not in the this. Okay, so 1 2 3 will take 1 2 3. Okay, so 0 minus 1 2. Then this is what? 1. Okay, so I will take here x and I will take here y also. Okay, 1 3 minus 1. So what do you want then? Y is equal to 1. Okay, so this is 1 because here sum is what? The sum is what? Y. Okay, x plus y minus x plus y is equal to minus x plus y sum. Okay, then twice x minus y. So see the equation. Minus x plus y is equal to minus x plus y is equal to 2. Then twice x minus y is equal to 3. Y is equal to 1 means what? Y is equal to 1. If you put y is equal to 1, then x is equal to what? Then 1 also. X is equal to minus 1. Y is equal to 1. X is minus 1. X is minus 1. But here if you take x is equal to minus 1, so this is minus 2, minus 1, 3. Something is wrong. minus 2. Okay, so twice x minus y. Twice x minus y is equal to twice x minus y is equal to 3 here. If your x is minus 1, so minus 2 minus 1 minus 3, but this is not minus 3. Okay, this is minus. So that means this x and y do not satisfy the third equation. So this will not. That means what is this is not. This is not. This is not. Okay. So don't check for the last one. Don't check for the last one. It is always belong to this. If you did your calculations correctly, then okay. Now we check whether this is belong to or not. Whether it satisfies this condition or not. In this way, you have to check whether this is in the linear combination or not. So see 113. 113. We'll check this. Is it in linear? Whether this x and y are exist or not. If this x, y, z are if x and values of x and y exist, right? Then we say that this is 111, 113 is the linear combination of this one. So this is what then first component is your y minus x plus 3y. Is it minus x plus 3y? Then what? Twice x minus y. This is your component. This your vector is what? 113. 113 is your vector. Okay, we'll check now this. What? Y is equal to 1 minus x plus 3y minus x is 1. Okay, twice x minus y is equal to 3. So y is equal to 1. Put y is equal to 1 here. So this is what? Plus 3. So x is equal to what? Minus x is equal to minus 2. So x is equal to 2. This gives. Okay. And if you put here x is equal to 2 and y is equal to 1, we get 3 here. Okay. That means this 113 is a linear combination. That means just check for first 3, whatever this one. Last one will be here. It will be here. But provided that you did the correct operations. Okay. Now, so for which value? Okay. Suppose I have given this vector. 1 to 1 to k, suppose 1 to k and 1 minus 2k. I want to find the value of this one. This vector is a linear combination of this one. Okay. I want to find the value of k now. So what is this then? Okay. What is this then? 1 to k is 7 what? X 0 minus 1 2 plus y 1 3 minus 1. Okay. So 1 to k. I want to find the value of this k. Okay. So this is what is first component is y minus x plus 3y twice x minus y. Okay. So your y is equal to 1 minus x plus 3y is equal to 2 twice x minus y is equal to k. You want to find the value of k. Y is 1. Put y is equal to 1. So this is what? 3. This is 3 and this is what then? Minus 1. So x is equal to 1. So we put the value of x x is equal to and y is equal to 1 here. So what we get? 2 minus 1 is equal to k. So k is equal to 1. Choose your option. K is equal to 1. Okay. Now suppose you are minus 2k. Okay. So for minus 2k, all are same here. Minus 2k suppose. And we want to find the value of k then. What here then? Y is equal to 1 minus x plus 3y is equal to minus 2 twice x minus y is equal to k. Okay. If you put y is equal to 1 here, so this is 3 and this is what then? Minus 3 minus 2 minus 3 minus 5. So minus x is equal to minus 5. Then x is equal to 5. And I'll put here then this is what then? This is what 10 minus 1 is equal to k. So k is it correct? Minus x plus 3y. Okay. So k is equal to what? 9. So k is equal to 9 will be your answer. So minus 2 is there. Okay. So your k is equal to 9 is the answer. In this way, you can find the value. If this is a linear combination of these two vectors, you can find k. K may be here then. 1 k, suppose 2, suppose 1 k. Any vector you can take 1 to k. And you have to find the value of this one. You have to find the value of k. This one. You can find the value of k like this. Okay. Okay, so just I have revised all those things. Okay, here. So about the subspace. Okay. Now in the next time we will see what do we mean by linearly dependent, dependent and basis. Okay. So that part we will discuss in the next lecture. Okay. So we stop here. Thank you.